Welcome to the SOLIDWORKS Masterclass. This is an advanced level tutorial series and this is part 1. In this lecture, we are not just learning which buttons to click. We are going to understand how weldments are used in real engineering, how professionals think while building them, and why weldments play a critical role in industrial machine design. You can also find links to my other tutorials on ANSYS Fluent and other engineering software in the description below. And if you need personalized one-on-one training or support in CAD, FEA, CFD or project and research assistance, our contact details are provided in the description. By the end of this lecture, you will clearly understand what weldments actually are inside SOLIDWORKS, why a skeleton-driven approach is essential, and how modeling decisions directly affect manufacturing, cut lists, and future design changes. This foundation is extremely important because everything we build later in this series depends on these concepts. Many people think weldments are just simple frames made of pipes or square tubes. But in professional CAD work, weldments are much more than that. A well-built weldment directly affects manufacturing accuracy, automatic generation of BOMs and cut lists, and how easily the structure can be modified when requirements change. That is why weldments are a core part of industrial machine and equipment design. In SOLIDWORKS, a weldment is created as a single part file, but internally it contains multiple solid bodies. Each body represents a structural member that will eventually be welded together in the real world. Because of this multi-body approach, SOLIDWORKS can automatically calculate member lengths, generate cut lists, and prepare manufacturing-ready data from a single model. However, weldments are not meant to replace assemblies. Assemblies are still used when parts are manufactured separately and then bolted or assembled together. Now, this is where advanced weldment modeling truly begins. We'll start with a skeleton-driven approach, see how structural members are applied and controlled, understand profile orientation, standards, and cut list logic, and then dive into weld joints using trimming strategy, gussets, end caps, and the real meaning of weld bead representation. These concepts are what turns simple frames into professional weldment models. Professional weldments always start with a skeleton-driven design strategy. Instead of modeling solids first, we begin with simple line sketches that represent the shape of the structure. This sketch is called the skeleton or the master sketch. Structural members are then applied along these lines. Because the sketch and the solid geometry are separated, the entire weldment becomes fully parametric. If the sketch changes, the whole structure updates automatically. This is the key to stable professional models. SOLIDWORKS provides standard libraries for structural member profiles, but selecting a standard profile does not automatically mean the design is optimal. In professional modeling, we must control the orientation of the profile so that faces align correctly for welding and fabrication. We also need to think carefully about corner conditions, especially when multiple members meet at the same location. Another important concept is member grouping, which helps manage similar members together and maintain consistency throughout the model. In real manufacturing, weldment profiles must follow industry standards such as ANSI or ISO. These standards ensure that the profiles we design are actually available in the market. We must also be aware of fabrication tolerances because small modeling mistakes can turn into serious welding problems. Each structural profile also carries metadata, which SOLIDWORKS uses to generate accurate cut lists. This is why weldments are deeply connected to cut list-driven manufacturing. One of the most critical tools in weldment modeling is trim and extend. We can let SOLIDWORKS trim members automatically, or we can define trimming logic manually. In advanced designs, we must carefully control member priority, especially at L corners and complex intersections. Different trimming decisions create different joint conditions, and they directly affect rebuild behavior and model stability. Understanding this logic is what separates basic users from professionals. Gussets are used to increase stiffness at welded joints, but they come with strict geometric requirements. They can only be applied between planar faces, and those faces must share a common edge. Gusset thickness is usually controlled parametrically, so it can be adjusted easily during design changes. It is equally important to know when not to use gussets, because unnecessary gussets increase weight,
cost, and fabrication time. End caps are often misunderstood as simple closing features. In reality, they play an important role in durability and manufacturing quality. End caps close open structural members, prevent dust, moisture, or debris from entering, and improve the long-term performance of the structure. They are commonly used when structural members remain exposed on both ends. Weld beads in SOLIDWORKS are cosmetic representations. They are mainly used for documentation and communication. Weld beads clearly show where welding is required in drawings, but they do not add structural strength to the model. They should never be confused with real weld geometry or used for analysis. In the next tutorial, we'll apply everything discussed here to a real example. We will start with a master sketch of a bicycle frame and convert it into a complete production-ready weldment. Structural members, trims, gussets, end caps, and weld beads will all be created step by step inside SOLIDWORKS. This lecture builds the mindset. The next one builds the model.